So now we're ready to tackle a pretty simple Laplace transform. Again, let's recall the definition where we have the Laplace transform of some function in time is equal to the improper integral from 0 to infinity of the integrand, which is the exponential decay function e to the minus st times that function in time, and we're going to integrate with respect to time, which should leave us with a function in s. Okay, so let's go ahead and see if we can calculate the Laplace transform of e to the alpha t. So wherever I see this function in time, I'm going to plug in e to the alpha t. I get the integral from 0 to infinity of e to the minus st times e to the alpha t dt. And I guess I could write this as the integral from 0 to infinity of e, and if I factor out a t, I write this as alpha minus s times t dt. So I just multiplied like bases and added the exponents, and in adding the exponents I was able to factor out a t, and that left me with an alpha minus s. And if we recall, with improper integrals, the thing is we're trying to get this thing to converge. And I know that if alpha is greater than s, this thing is only going to grow, because then this exponential just this alpha minus s is positive, and then the time would just grow and grow, and the exponential would grow. But then the area under the curve would just diverge; it would never converge. So we'll have to stipulate that s must be greater than alpha. So if s is greater than alpha, that forces this argument to be negative, and we'll have an exponentially decaying function. Okay, so let's go ahead and see where we are. Let's go ahead and write this as the limit. I'll say is j goes to infinity of the integral from 0 to j, and here I have e to the alpha minus s t dt. And if I integrate that, let's see, I get the limit. J goes to infinity, and again, if I integrate e to some argument times t, is just 1 over that argument, e to the alpha minus s t, and I want to evaluate that from 0 to j. So let's write the limit as j goes to infinity, and let's just use the evaluation theorem, and then so I'll apply the upper and lower limits. So I get 1 over alpha minus s, and at j this becomes e to the alpha minus s j minus 1 over alpha minus s e really to the 0, and e to the 0 of course is just 1. And since we know that s is greater than alpha, then this becomes a negative value, so this becomes e to a negative constant times j. And irrespective of how big the constant is, the limit for long times t should drive this entire piece to 0 when we apply the limit. Okay, so I'll get that this equals the negative of 1 over alpha minus s, or 1 over s minus alpha. So we have that the Laplace transform of e to the alpha t transforms to 1 over s minus alpha, provided that s is greater than alpha. Conversely, if the Laplace transform maps to 1 over s minus a on s minus alpha, then the inverse Laplace transform of 1 over some s minus alpha should map back to e to the alpha t.